Alright, so in the first video, this is where we left off, and I showed you that this type of motion has zero average velocity. I watched my recording and I had called this average speed accidentally. I wrote it correctly, but I said it incorrectly, so please disregard that. This is average speed, this is average velocity. But before I move on, I want to quickly show you how this graph would be made, because it might look like this object is being thrown like a ball as a projectile, but this is really 1D motion. And I found this applet, and this is the actual motion of the ball. I'm going to do a rise and fall like this graph, and so you're going to see the ball go, and the graph will go up accordingly. So when the ball is here at 2.5 meters, it'll be here at 2.5 meters, but it would have taken this amount of time to reach that. So time is kind of spreading the path out, but it's really just a one-dimensional motion. Take a look. See that? One more time. It's going straight up and straight down. This was going straight up and then straight down, but it was being pulled along by the time it took, which was 2 seconds according to this. Okay, this will disappear. Alright. So, continuing on with my list of things I wanted to talk about. Oops. Let's just see if I got enough space here. Alright, good. Continuing on with the things I wanted to talk about. The next on the list was instantaneous velocity. Alright, so instantaneous velocity is related to average velocity, but of course it happens not over a long period of time, but it happens at one infinitely small moment in time. Those of you who have taken calculus will know what this means probably right off. Those of you taking calculus now, I'm guessing haven't gotten there yet. Instantaneous, whoa, is that right? That's right, instantaneous velocity. Just so you know, I still haven't figured out why this decides to not write. I don't know whether it's not writing at a certain time because it's thinking or something, or it seems to me like certain places. See, it could go there, but not there. What's so special about this place? Maybe it's too close. Anyway, that was enough time wasted talking about that. Instantaneous velocity. Symbolically, it looks like v equals the limit. Again, calculus folks, this is familiar. Limit as the change in time approaches 0 of the change in position compared to the change in time. And as this approaches 0, then the way we write it, this delta, this change in, becomes a d because this change in is so small that you couldn't even measure the length. It probably sounds weird right now, but when I draw the picture to show you what's going on, that might become more clear. This is calculus. Oh my god. So, let me draw a graph here. And let me make a curve like that. That's probably going to suffice. And let's have a non-zero delta, a non-zero change, meaning our change in x, don't forget this is the x-axis, meters, and this is the t-axis, time. You know, I think I'm starting to figure it out. I think if you get too close to an earlier pen mark, for some reason it's not allowing it to write. Just a hypothesis, but more data will prove me wrong or right. Anyway, so we have this graph, and we have a non-zero delta x. In fact, our delta x is this big. Here's x final. And here's x initial. So it's definitely not 0. Of course, our delta t is not 0 as well. It goes from here to here, right? And we can represent the average velocity with a line like we did before. And that line would look like, oh, I messed up. Let's start over about here. There we go. Alright, so the average velocity between these 2 points, wow, that's crazy, is this, the slope, remember, of this line. Well, calculus speak, this is saying as delta t, as the change in time approaches 0. What that means is this distance from here to here approaches 0, or this line right here slowly moves little by little this way. Or in other words, the dot on this graph that represents, the point on this graph that represents this time moves back, and as you can see accordingly, the corresponding x coordinate also gets shorter. And what you notice, if you draw lines, let's see if I can eyeball this. This one probably looks good. The lines get, alright, and I think I'm gonna go like here. This is very rough. Pardon my inaccurate pen drawing skills. Maybe like that. Oh, that's horrible. Let me just drag that down. Nope. Pen. This one should be down like that. And then up like that. What I'm trying to show you, somewhat successfully, is these all right down here should be on this point. Remember this first point I drew right here? But these should be on these corresponding points moving down. And what you'll notice is eventually, as this point gets closer and closer and closer to the first point, so that the change in time here is 0, you're going to get what's called a line that is, I don't think I have a line that is tangent to the graph at that one point. Tangent meaning it only intersects once. See how all these intersect twice? 1, 2, 1, 2, 1, 2, 1, 2. But as this gets closer and closer, it intersects only once. That's tangent, and that is the instantaneous velocity, or the slope of this tangent line now is your instantaneous velocity. So the average velocity becomes more and more instantaneous as we slide down this curve until we reach the point where the distance between these 2 points is essentially 0. It's actually not 0, but it's what we call infinitely close to 0. Try picturing that. It's going to take a lot of brain power. I don't think anyone can really truly picture it. So that's instantaneous velocity. And so you're going to learn more about this in calculus, but you're going to need this for some of your homework problems. There's some rules in calculus on how to find this dx dt for certain graphs. Assuming this is part of a parabola, we might have a graph that looks like this. Normally x is y for the y-axis, but this x is now on our typically y-axis. X equals, and normally this is our x variable on our x-axis, but t is on the x-axis, so t is going to be our variable. X equals at squared plus bt, that's a t, plus c. Now, in calculus speak, we want to take, we want to basically, how should I say this? We want to, well, what it's called differentiation. We want to differentiate the x function with respect to t. I'm going to try to say this as clear as possible for those who have not taken calculus yet. Basically what this is doing is you're taking this graph, and this right here is essentially sliding the 2 points, one point being here always and the other point being this point, sliding them closer and closer together so they become infinitely close. And when you do that, you get your velocity. I'm just really rewriting v. Your instantaneous velocity is dx dt. So equals v. And there's a rule for doing that. I'm just going to show you what it is, and then I'll show you how I did it. So this over here is going to turn into 2at plus b. How did I get that? I'm going to show you this, and gosh, time flies. I'm going to have to stop this and go to another video. So how did I go from here to here? I essentially did one term at a time, and the formula is if you have something like a t to the n power, when you take the derivative of this, it becomes n a t to the n minus 1 power. So let's see how that worked. Here we had at squared, n is 2 here, so we bring the n to the front, just like see the n here, we bring an n to the front, not, in this case it's 2, so there's the 2 here, a t to the n minus 1, or 2 minus 1, and 2 minus 1 is 1, we don't have to write the 1 here. So that term is taken care of. Now what about this bt term? Well, n for this term was originally 1, so we bring that n term to the front, so there's the 1 here. And then this becomes n minus 1, or 1 minus 1, which is 0. And t to the 0 is also 1. So we're just left with b times 1, or b. I feel like I might have explained that a little quickly. Try just watching the last minute or so of this video where I explain this. Try watching that a couple times if it's not sinking in. And if you don't quite get it, I can show you again in class. Alright, I'm going to stop here, and then I have a little more to talk about actually. Wow. Alright, see you in a sec.